Hi, I'm John Roberts. I'm a student in Jonathan Fan's group at Stanford University. Today I'll be talking about multiple tunable hyperbolic resonances in broadband infrared carbon nanotube metamaterials. As background, I'll introduce aligned carbon nanotube metamaterials and talk about some of their features, including broadband hyperbolic dispersion. I'll show how we can use that hyperbolic dispersion to confine infrared light in deeply sub-wavelength carbon nanotube resonators. Then I'll show that individual carbon nanotube resonators can support multiple hyperbolic resonances, including higher order modes. And finally, I'll talk about how multiple resonances enables broadband extinction in the infrared with tunability through doping control. The material system that we're talking about is globally aligned densely packed carbon nanotubes prepared using a vacuum filtration process. This process was invented by the Kono group at Rice University and has since been developed by our collaborators at IBM and in our group. We start with carbon nanotubes in solution and pull a vacuum on the opposite side of the filter membrane. While the solution is filtering through the membrane, the carbon nanotubes self-assemble into a horizontally aligned film on the filter surface. In this top view SEM, you can see that the carbon nanotubes are horizontally aligned. They're lying flat on the filter membrane. And in cross-section, you can see that they're very densely packed. And the film can be tens to hundreds of nanometers thick. This is an interesting system for nanophotonics because of a few interesting features. First, we can change the carrier concentration in carbon nanotubes through either doping or gating. In aligned carbon nanotubes, it's also possible to achieve ultra-strong exciton cavity coupling either with an intrinsic carbon nanotube plasmon or with an external cavity. Globally aligned carbon nanotubes can also be used for polarization-sensitive photodetection. Carbon nanotubes are suitable for thermal emission because they have a low thermal mass and good stability at high temperatures. And finally, because the vacuum filtration process creates a large area film with easy transfer to arbitrary substrates, it's a very flexible platform to work with. So in this work, we're showing that in addition to these features, carbon nanotubes are broadband hyperbolic metamaterials in the infrared. So we're treating the carbon nanotubes as a uniaxially anisotropic but homogeneous medium that has one dielectric function along the nanotubes and another dielectric function in the directions perpendicular to the nanotubes. In using this model, our collaborator at J.A. Woolham has performed spectroscopic ellipsometry on these carbon nanotube films, and the results are shown here. The solid red line is the real part of the dielectric function along the carbon nanotubes, and the solid blue line is the real part of the dielectric function perpendicular to the carbon nanotubes. And you can see that in these two wavelength ranges marked in green, one in the mid-infrared and one in the near-infrared, these dielectric functions have opposite signs. So this is hyperbolic dispersion, and it's usually achieved by combining metals and dielectrics in anisotropic metamaterials, or by using an anisotropic crystal that has phonon resonances. So as hyperbolic metamaterials, carbon nanotubes are fairly unique. In these wavelength ranges along the nanotubes, it's effectively metallic, and in perpendicular directions, it's effectively dielectric. And another unique feature for carbon nanotubes is that we can control the carrier concentrations through doping. So these are the same the dielectric functions measured after doping by exposure to nitric acid vapor. And what we can see is that because the exciton has been quenched and the carrier concentrations are increased, that the hyperbolic wavelength range has blue shifted and is now wider in frequency. So now we have a hyperbolic wavelength range that covers much of the mid-infrared. And in the rest of this work, I'll be talking about things that we can do in this broad hyperbolic wavelength range. So just to review, optical hyperbolic dispersion has been very heavily studied, and the best way to understand the consequences of hyperbolic dispersion is to look at isofrequency surfaces in wave vector space. In an isotropic dielectric, you can have one wavelength in any direction, but in a hyperbolic material, the allowed wave vector surfaces become open hyperboloids. So in certain directions, you can have very large wave vectors corresponding to very short wavelengths or high confinement in a hyperbolic medium. So to study this effect in the carbon nanotube system that we're studying, we use an experiment where we pattern many arrays of ribbon resonators into a large area film of carbon nanotubes, and we perform infrared spectroscopy to look at the resonances of these ribbon resonators. And we have 2 degrees of freedom to work with. The first is the resonator width, and the second is the angle of the ribbon relative to the carbon nanotubes. So these are top view SEMs. And then these are experimental extinction spectra offset for clarity with the incident light polarized along the carbon nanotubes. And what we see is that as the And these are all ribbons of a fixed width, and we see that as the cut angle goes from 90 degrees perpendicular or normal cut ribbons relative to the carbon nanotube, as the cut angle decreases to the more diagonal, that this resonance peak that we see redshifts dramatically. And one way of understanding this is that this means that effectively the ribbon of a fixed width is resonant at a much longer free space wavelength, so it's resonant at a deeper sub-wavelength scale. And this is the result of hyperbolic dispersion. And the way we understand this is by looking at this model where we think of a ribbon as a Fabry-Perot resonator that confines hyperbolic waveguide modes in the carbon nanotube film. So in this cartoon, I'm showing the hyperbolic waveguide modes that's confined in the film. And in these top view cartoons, what we're looking at is the wave vector of this waveguide mode. And the point here is that because these nanotube films are in-plane anisotropic, when we go at an angle to the carbon nanotube alignment axis, these wave vectors can access high K parts of the in-plane hyperbolic frequency surface and become very deeply confined. So in our Fabry-Perot model, the carbon nanotube ribbon fixes the magnitude of the resonant wave vector based on the ribbon width and the direction, because the resonant wave vector is always normal to the ribbon direction. So then the way we understand the redshift that we see in the experimental spectra is that the redshift occurs because at off-normal cut angles, we're accessing high K points of the hyperbolic isofrequency surface, and the ribbons become resonant at more deeply sub-wavelength scales. Now I'll introduce our work showing that individual carbon nanotube resonators can actually support multiple hyperbolic resonances. And this is motivated in part by some applications that are compelling with carbon nanotubes. So it's well established in metal plasmonics that individual resonators can support multiple resonant modes at different frequencies. In the infrared, you can use this phenomenon to create resonances at several wavelength ranges where there are molecular spectra that you're interested in sensing. And carbon nanotubes are compelling for this kind of infrared spectroscopy because they have a broadband hyperbolic frequency range in the infrared. Also in the infrared, you can control the properties of thermal emission. And this is an example of using, in this case, multiple resonators to create multiple thermal emission bands. But you could imagine with a carbon nanotube metamaterial that has two resonant modes, we could control the spectrum of thermal radiation. And finally, because there are detector mechanisms based on carbon nanotubes, we could use carbon nanotube multi-resonant absorbers to create spectrally selective detection. Experimentally, we measure this appearance of multiple resonances when we look at resonators that are comparatively wide. So this is a series of extinction spectra, again, for polarization along the nanotubes, for normal cut ribbons with widths increasing from 160 nanometers up to 2.5 microns. And we see that the original resonance peak is redshifted, and then at certain resonator widths, higher order modes begin to appear in the spectrum. And one thing that we can do, because we have the effect of dielectric functions, is we can model these ribbons using simulations in theory. And when we find the simulated extinction spectra, we see that there's very good agreement. And in particular, now we can use the simulations to try to look at the field profiles at a few of these resonances to understand their origin. These are the field profiles of 3 resonant modes in the same ribbon at different frequencies. And we can see that as for these higher order modes, there are more nodes in the field inside the ribbon. And this gives us a first clue as to the origin of these resonances. To understand rigorously the origin of the resonances, we perform a similar study on the properties of many ribbons with varying widths and cut angles. This is a series of ribbons with the same width as the cut angles change, and you can see that for more and more diagonal cuts, the higher order modes also redshift. This indicates their hyperbolic origin. And using our Fabry-Perot picture with many ribbon arrays of varying widths and cut angles, we can construct dispersion relations of the hyperbolic waveguide mode. And we do this by knowing the frequency is fixed by the resonance, and the magnitude of a wave vector is fixed by the Fabry-Perot condition. In this case, it's some multiple of pi minus a reflection phase that we estimate numerically divided by the ribbon width. And we hypothesize that the mode orders here are 1, 3, and 5, because those are the mode orders that radiatively couple to free space. And when we do this, we find that for a given cut direction, all of these dispersion relations from the different mode orders collapse onto a single line. So you can think of these resonances as higher order Fabry-Perot resonances of the same hyperbolic waveguide mode, which is fitting in different numbers of half wavelengths into ribbon width. And another effect that shows up here is that for the more diagonal cut angles, the dispersion becomes more deeply sub-wavelength. It moves further past the light line. And this is again because we're sampling high K points on the isofrequency surface. So understanding the origins of these modes, one thing that we can do is we can use these resonances to engineer broadband extinction in the infrared. So these are the spectra of one resonator array before and after doping. Before doping, there are 2 plasmon peaks and a exciton peak. And after we dope them by exposing it to nitric acid vapor, we measure 3 extinction peaks. And based on the field profiles and simulations, we see that these are the same modes that we had been studying earlier. So our understanding is that this is the presence of multiple resonances is one way to create broadband extinction. And because we can reversibly control the doping, it provides a degree of control over the extinction. So to conclude, carbon nanotube metamaterials have broadband hyperbolic dispersion in the infrared. And we've shown that these metamaterials can support multiple resonances that provide extinction, spanning the mid-infrared with control through doping. One thing I should mention is that this happens in a particularly important 3 to 5 micron atmospheric transparency window. And with that, I'd like to conclude. I'd like to thank our group members, my advisor, Jonathan Fan, our collaborators, and our funding sources. Thank you.